For the opportunity to talk about my work. I believe this one is not going to be really related to complex networks. I'm going to stay on the dynamical process of this workshop. But the idea is to try to explain some numerical findings that I had in my PhD with Professor Ibere. And also, I mean, the idea now is try to apply this numerical framework to try to understand some dynamical process in complex network as well. So let's just start with the idea of recurrence, right? So the idea of recurrence is just basically it's corrupted here, but I don't think it's a problem. But anyhow, so if we have a trajectory that's defined on a phase space, then if this trajectory returns to some point that already passed before, then we have a recurrence. And this definition of a recurrence is different from the definition of Poincare recurrence, which is just the neighborhood of the initial condition that you put. So it might return to the neighborhood, like epsilon neighborhood of your initial condition, but now I'm exploring just a general type that if you just evolve a trajectory and it returns to somewhere that it passed before, then it's a recurrence for me. Then we can write this recurrence matrix, which is just binary one if we have this recurrence, and then it's zero otherwise. And then every entry of this matrix, we can show this as we define this recurrence plot. The recurrence plot is essentially the color dots is just a recurrence that you have on your trajectory, and then this is just a few different examples of time series that you can have. Essentially, this one I want to call your attention to the middle one, because this one is from a chaotic system, which means that you don't have some regular structure, which is the patterns of these recurrence plots is very important for me. So the idea is that you are changing the structure. The structure of your time series is changing, and then you can see that on the recurrence plot. So I just put some other examples here. It's nice that when you have some periodic trajectory, you have some beautiful structures here as well on the recurrence plot. And also, I want to call the attention for this C example, that we have these really recurrent piece of the time series, and then we can see exactly on the same point this tiny square that appears on the recurrence plot. That's very important for me. So essentially, since we have a recurrence matrix, we can look at some measurements that you can make on this matrix. The simplest one is just the rate of the recurrence. Then you just sum all the ones in the matrix, and then you just divide it by the size of the matrix, which is iteration by iteration. It's just the length of your time series. And then we have what we call recurrence rate, which is essentially just a percentage of how many points are black colored points. So that's the part of the recurrence, but I need to take you back a little bit for classical mechanics. Is just the idea of chaos periodicity and also Hamiltonian systems, because I'm very interested with these Hamiltonian systems that you can write as a sum of a Hamiltonian that's just integrated, just very boring, but also you can put epsilon parameter here that you can actually create some periodic perturbation of your Hamiltonian system. Then you have a thing. It's actually very important that to keep in mind that I'm talking about conservative systems. Also, all of my phase spaces, all of my study is so when you look on the phase space, you're not having a tractor there. It's just it's something that is happening on a finite time, or it's something that is happening on as long as you want to iterate the system. So the idea that when you have these other part of the Hamiltonian, you can create resonances, because you have a phase related to the first part, and also another phase related to the second part. And then when you actually create this resonance, then you create a lot of chaotic regions on the phase space. That's very important for me. So the idea that, so we are talking about Hamiltonian systems, and then you can also, just because of these phases that are associated with the dynamics, you can create a Poincare section and then just look at the map of these iteration of your Hamiltonian systems. So when you look at these phase spaces, they're a mixed type because they're a coexistence between chaotic regions and also periodic regions, right? So it's cropped here, but it's very important for me to discuss this phenomena. It's a nonlinear phenomenon that only happens on the Hamiltonian systems, which is called stickiness. And I'm going to give some examples. So the idea is just that you have a chaotic orbit that starts on the chaotic portion of the phase space. You evolve it, and then at some point of their evolution, it gets trapped around some island, some periodic region of the phase space. And when it gets trapped, you might think that, all right, so you're diffusing quite all right at the chaotic region, but all of a sudden your diffusion is very strict. It's very narrow in some part of the phase space. So I'm going to try to look at that only by numerical means, numerical procedures. But the problem that I wanted to tackle is the following. So we know that it depends. So if it's going to happen, so the trajectory is going to experience stickiness or not, depend on the parameter that you put on the map, in your system, and also on the initial condition that you may put on your simulation. So I'm going to tackle the following. I'm going to tackle which initial condition is going to experience these nonlinear phenomena. So just to make an example, this is a classical phase space that you see on the literature. This is the standard map, Shirkov standard map, and so these are just the time series of this conjugated momentum. And essentially, we have these two orbits. They are very close to each other. But the idea of the red orbit is just, it didn't get trapped anywhere. But the blue orbit gets trapped at some point on this time series. And then it just behaves a little bit of quasi-periodic, and then it just gets out. So essentially, this is an example of stickiness, because we have these trapped behavior. And so I was talking about recurrence, right? So let's look on these trajectories, which is how is the recurrence plot of these trajectories, right? So the red one is very chaotic, so we just have recurrence by chance, it's just some small dots. But the blue one, actually, we have a very nice quasi-periodic structure, and then we see on the recurrence plot. And then this thing is what kind of made me thinking, because these, when you compute like this recurrence rate, how many recurrences you have in this trajectory compared to this one is going to be larger than this one. And then let's just compare for a very large ensemble of initial conditions. And then when we have a large number of the recurrence rates, then we have the initial condition that give us a trajectory that's very recurrent. So that's the idea. So I'm going to apply this for the time-dependent potential well. I'm just, because of the time, I'm not going to explain the full details of the model. But the idea is just that you can make a Poincare section and then just look at this map, which is cropped. This is like a dimensional energy, and also you have a dimensionless phase. And then you can just plot the phase space, which is essentially like this. So this black region is the region of the chaotic dynamics. And the black region means that when you start with some energy larger than 1, you can just deviate this energy, just evolving some trajectory which is chaotic, until like around 4. So your energy can grow, essentially, because we are in this specific type of systems that are conservative and also time perturbed. Then you just, in average, you can gain energy. So that's kind of the idea. So we are going to essentially give a recipe how to detect stickiness in these type of systems. So we know that this is a mixed phase space with chaos and irregular structures. Then we know that we know exactly the initial conditions that give us some for sure chaotic orbits, and then we just evolve these chaotic orbits. And when we evolve that, we can compute the recurrence matrix. If the recurrence matrix has a lot of ones, then we know that we are in a chaotic trajectory that stays very recurrent, at least for a while. So that's the idea. So let me just, let me just say to this one, which is essentially, I'm putting, so let me just explain this one first. So this one is, I am fixing an energy that I'm giving to all of my initial conditions, and I am varying the initial phase from 0 to 2 pi, and then I'm putting m, which is the number of initial conditions, so there's 1,000 initial conditions here. So in this distribution, meaning what I'm looking at is just the recurrence rate for each one of these trajectories, right? So when we have a peak on this distribution, it means that this specific initial condition has a lot of recurrence. And then I just look at the phase space of this specific trajectory. And then when I start, the color scale actually shows the time as well. So when I start, it's just the beginning, it's black dots, and then it just gets trapped around this main island, and then it stays there for a long time, actually. Because when we look on the phase space of the energy, for example, I am starting with 1.10 on the energy, so it's chaotic, so it needs to just visit all the chaos, or the chaotic region, and then all of a sudden it gets trapped for a very, very long time. And that's the phenomena that I was interested to study, the stickiness, which is, I mean, this one is cropped as well, but the idea is just when you plot the recurrence plot of these specific trajectories, then exactly at the same time that your time series gets very quasi-periodic, then we have this very nice structure on the recurrence plot as well, which meaning that we have a very strong recurrence patterns. So essentially, I did that for the other parameters, because this model here, you can plug some parameters here that is related to the physical meaning of the potential and everything. And so essentially, that's it. I'm just changing this number NC. So I'm doing this for NC equals to 2.5. Then I can look at this peak and then just plot the phase space with this specific trajectory. And the same thing happens. We see stickiness, we see chaotic behavior, and then we see stickiness. This one is nice because we have already some recurrence at the beginning, which is this black squared here. And then all of a sudden, it starts with like a very, very strong stickiness, and then there's another part of the recurrence plot that's not showing here. But I did the same for another parameter as well, just to show that it's happening when you just change the parameter. But I just want to summarize and kind of try to convince the audience that this is somehow could be connected with suitable abstractions, so to say, to analysis of a large amount of data. Because when you have a large amount of data, you have a lot of time series, you can look at this distribution, which means just that you have to compute this recurrence matrix, and then kind of these peaks on this distribution, meaning that these specific time series show some so to say, not average behavior, because there's average in these distributions, and then you can compute somehow like a sigma deviation from the average, and then you just look at these peaks. And these peaks, I'm kind of saying that these peaks are anomaly behavior. Like somehow in your large amount of data, you can just look at these distributions throughout the recurrence analysis. And then in our case, it's just initial conditions, because initial conditions make us the trajectory that we are analyzing, right? And then we can just yeah, I mean, it's not going to be good if it's big, because the matrix is n by n, so n squared. Then, yeah, I mean, yeah, not necessarily. These ones are 10 to the 4 is kind of big, right? but it's 10 to the 4, and then we already see like a lot of stickiness, essentially just for these initial condition, right? Depends when you start, right? Where you start, yeah. If you start like somehow close to the island, then somehow it could get trapped. I don't know. Depends on the manifolds that are pushing them by. Yeah. But yeah, that's something that we are actually doing. So just to summarize, it's just this is the paper that I discussed this procedure, that how to detect stickiness. I'm just calling your attention for the finite time recurrence, because that's the point of Thiago. It's just we're not looking, I mean, the point of you have to define some interval, and in this interval, then you can say, so which initial condition has stickiness in this interval. So it's a finite time analysis somehow. And I just want to finish acknowledging my collaborator, Flávio from the Instituto Federal de Minas, which is a neighbor state of São Paulo, which with better food, I would say. And and then I just finished. Thank you very much for your attention.